Hey everybody, this is Larry. This is day 16 of the September Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord, let me know what you think about today's poem when it wants to load. Alright. Yeah, beginning of the week, I just finished my 5 mile run. Just a very easy, lazy run. Just to kind of, get my blood flowing and stuff like that. Yeah. A little bit tired. Could be less tired if this poem comes up. Okay, well, maybe not. It's a heart. So we'll see how it goes. Yeah, let's go. Today we have 2197. We place non-coprime numbers in an array. Alright, you're given an array of integers nums. Perform the following steps. Find any two adjacent numbers in nums that are non-coprime. What is coprime? We'll read it later. If no such number found, stop the process. Otherwise, delete the two numbers and replace them with their LCM. Repeat them as long as you can. Return the final modified array. Can be shown that replacing adjacent non-coprime numbers in any arbitrary will lead to the same result. Okay. So you have to find basically two numbers and then just keep on doing this operation. Now, I don't know why this thing isn't quite loading, given I already finished reading. But maybe that's okay. Maybe we'll refresh. N is 10 to the 5th. So the naive solution, the naive attempt, while I refresh this, the naive attempt might be for it to load. What is going on with Leetcode? Okay, there we go. The naive attempt may be just to n square and then with another while loop, n cube would be the easiest thing to do. Of course, with n cube, that is not the case. Oh, sorry, with n is equal to 10 to the 5th, n cube is going to be too slow. Right, so yeah. Okay, so let's kind of see what coprime means. With the GCD, okay, so wait, are they coprime or non? Oh, they're non-coprimes. Okay, so that means that if two numbers are relatively prime, then we don't do anything. Okay, so what does it mean for numbers to be non-coprime? For numbers to be non-coprime, it means that it shares divisors with another number, right? That's basically another way of saying it, because the GCD is of two numbers are greater than one, right? Yeah. So we have to figure out some way to do this in a quicker way. And yeah, what does this look like anyway? So 4 and 6. I mean, I think if you were able to do things quickly, one number at a time, then even if we do log n or something, then n log n will be fast enough, right? And so I think that's basically the idea that we want to do, right? Is that maybe we would say for every prime is equal, or it doesn't even matter, for every divisor is equal to 2, if there are multiple numbers, we combine them, right? And then we just keep on going. I don't think there's really that much trickery. And as long as we're able to combine two numbers at a time, then yeah, if you're able to remove, basically combine two numbers and get one number back means removing one number, right? Kind of. So that allows you kind of, if you're able to do one search in a quick enough time, then you only need to do up to n search to search and replace or whatever to get to one element, which is going to be the worst case, right? Okay. I don't know how to quite describe what I want to do today, but the idea it is what we're going to say, which is this prime CIF idea, right? And the idea of prime CIF is just, I mean, for this particular one, it wouldn't really be a prime CIF necessarily, but we can do something like for x in range up to some number max, right? So there are two ways to do this. One is do it once for every problem, and then two is to pre-calculate the divisors, or and then just do the divisors that way. Maybe that's a little bit better. I'm trying to think. Like if we try to combine 6 and 4, right? So one is 2 times 3 and the other is 2 times 2. Well, the GCD is 2, so then we combine them to just 24, right? Or 12, sorry, which is fine, right? But how would we re-represent this divisor? And that's the thing that I'm trying to figure out. I think the prime CIF is probably the way to start, and then if we need to optimize, we can optimize. Yeah, we could maybe get the variation with just divisor CIF. I think one thing, I guess it actually doesn't matter, because I was thinking about how to combine them in a good way, but as long as two numbers have a common divisor, it doesn't matter what the number is, we could just calculate it, right? So I think we should be good, actually. So we could actually even use the prime version. I think it shouldn't matter. I mean, I think divisor may be a little bit cleaner, but the idea here is that the idea behind the CIF, sorry, I'm not kind of jumping over the place because I'm still trying to verifying in my head, right? The idea behind the CIF is that you have a lot of numbers, right? And then to get, well, what is a prime number? Well, the prime number is a number that has no multiple, or it's the only divisors of 1 in itself, meaning that there are no divisors smaller than it, right? So that means that when we say, okay, well, let's just ignore 1 for now, whatever, right? Because 1 is whatever, and then we have 2 we know is prime, so then now we take all the multiples of 2 and then we move them from the list, right? Because we know that 2 cannot be, well, prime. And now we have 3 is the next number, so then we remove all the 3. In theory, there should be a 9 here, and then you remove it, and so forth. That's kind of the prime CIF. The reason why this works, I mean, it works anyway, right? It works because you literally you're sieving through, you're removing multiples one at a time. But the other thing about that is that if you look at it, then now if we remove every 1 over 2, like every second number, and then every third number, and then every fifth number because it's prime, but you can also just, you know that this number is strictly bigger, and all this apparently sums to n log n, and that gives you an upper bound. The lower bound, I mean, the upper bound can be tighter than that because, as I said, you can actually remove stuff like this because, well, we don't force, not a prime. In any case, it should be okay. So yeah, so then now we can say, let's just say max is equal to the biggest number, which is 10 to the 5th. So maybe we go 10 to the 5th plus like 5. I would just add a little something. And then we just go y is, we could say 2 times x, right? While y is less than max, then we increment x, and then we do something like divisor of y append x, right? Oh, is that how we do it? I forgot how we wanted to do it. No, actually, I mean, we could do it this way, but yeah, we could just write the smallest prime, right? Or the biggest prime, it doesn't really matter. But prime sub y is equal to x. And maybe prime is not quite a great number, but it just means that, I forget what they call it, like largest prime or something, maybe. But basically the idea is that sorry, 2. The idea is that prime sub I is equal to the the largest prime that is smaller than I, or that divides I, and that's it, I guess. And yeah, and this is basically what it does. And then now, as a result of that, then you can kind of keep on going, right? So for x in nums, we could say prime is equal to just an array list. And then while x is greater than 1, we can say x we divided by prime sub x. And then, yeah, p dot append prime sub x, and then that's it. And it should go all the way down, right? The idea here is that, like, for example, you have a number that's, I don't know, 2 times 2 times 3 times 3 times 3 times 3. It would basically get 3 as the biggest, and maybe just add a times 5 for some reason. The biggest prime is going to be divided by 5, and then after that it's going to divide by 3, divided by 3, divided by 3, so then it's just one at a time in this way. I don't know, depends on which way you would like it to go. And for this particular problem, I want to say it doesn't even matter. You don't need to know the number of you don't need to know the number of dupes, meaning that you have, for example, 4. You don't need 2 times 2. You just need 2, because if a number, if this number and another number has a common factor of 4, they also have 2. So then they're already non-coprime, or whatever they call it, right? So in that way, then we can just make it into a set. This makes it slightly faster, maybe. Yeah. But actually, maybe it doesn't even matter, because then now, you could rewrite this another way. But then now you could write for, I don't know, another one for j and p. So for every prime, we want to say, how do I want to write this? I mean, there's so many ways to write this, but now, so I don't want you to think that the way I'm writing now is the only way to solve this problem. I mean, there's probably like 80 different ways to solve this. They're way similar, probably all of them way similar, but there's so many ways to solve this. Because you could finish pre-processing and then do it one at a time. You could do it incrementally, which I'm tempted to do, and all these other things, right? For example, you can maybe write something like answer, right? And then now we can say for j in p, we can maybe write first is equal to some lookup table, and basically if j is in first, and what I want to do now, and it may not even be the best way, but I just kind of feel like it, but it's just basically the first index in answer that has this prime in its divisor, right? Yeah, I think that's right. And then now here, yeah. Also, I want to say, like, for example, you can also do what do we call it? At this point, you can also do like union find type things. That's probably cleaner, actually, to be honest. But I mean, like I said, there's so many ways to do it. We'll play around with it and we'll see. But yeah, if j is in first, that means that another number is found. First of j is going to be equal to that previous index, and then we have answer of index is the previous number, x is the current number, so then we want the GCD, right? And then we want the answer of index, we want to multiply it by the GCD, right, to get the LCM, right? Wait, to get the LCM, it is x plus, or x times, so it's going to be, I'm wrong, by the way. This times x over g, right? So that's the new GCD. And then in this case, though, that means that found is equal to true. Then we could say found is equal, if found then we break or something like that, right? But it also means that now we can go through this particular P and then add it to the answer, right? Because then now, yeah, for K and P, we say if, I don't know if this is the best way to do it though, honestly. If K not in first, then answer of K, oh no, not answer, oops. First of K is equal to this current number, which is the index, right? Basically, we're just taking all the primes that the other, because we're kind of in a way merging them together. So we're taking all the primes and then adding them to it. One thing I would say, by the way, is that the number of distinct primes for 10 to the 5th, it's like 10 or something, maybe more. I actually don't know. Maybe either 10 or 13 or 14, something small, right? So that's why this is okay, right? It's not fastest, but it's okay. We might have to optimize it, but that's some of the rationalization on whether this is fast enough. Okay, and then now if it's not found, then and this is a prime to all the previous numbers. Actually, I don't like the way I'm doing it, because I feel like I messed up here actually, because I feel like you can have something like 2 and then 3, right? Of course, 2 and 3 are relatively prime, so they're not going to add to each other. But then later, if you get a 6, 6 will only merge to the 2 to get a 6. But then now we have to merge again. So so I think I messed up here. I think what I actually want to do is what I said earlier with the union find. So let's actually rewrite this a little bit. Right? How do I want to rewrite this? Well, okay. So instead of, okay, no, this is fine. P is fine. All right. Yeah, it should be fine. I'm trying to think how to get the final number, and I think you could just do it afterwards. You don't have to do them live, as you process them. You could do them afterwards. So I think that should be fine. Right now, I'm just going to write out the union find code. Not going to go over it today. It is a hard problem, and it is a late day. But we do have, I mean, probably even the last time I did it, it may have some, I don't know, I don't remember it. But yeah, we're going to do union find. So here, maybe we have the parent is equal to but union find is one of those things where there are a lot of videos for it, so I don't feel bad for not going over it today. Hopefully that's okay, because it's possible that this is already going to go a little bit late, 18 minutes. Yeah. And you could maybe call this template, maybe not. I just have done this so many times that yeah. Okay, so what does this mean, right? That means that for every prime that is for this number, you're kind of connecting it with all the previous numbers. And I think maybe I'm not drawing this well, and the union find doesn't make sense, but the idea here is this idea of transitive property, right? And what I mean by that is that, let's say you have a circle. Because basically you have, say, here, you have numbers that are divisible by 2, you have numbers that are divisible by 3, and maybe you have numbers that are divisible by, I don't know, 5, right? And then now, let's say you add a 10, then what happens? Well, 10 is obviously you go to 2 times 5, right? That means that 10, whatever it is going to merge with some number there, and then get a bigger number that has both 2 and 5. That's the definition of LCM, right? So then whatever they are going to have some 2 and 5 component. And as a result, now these two have to combine again. So basically another way of saying it though is you go to, if all the primes, we combine them together in a union find. In a same set that are no longer disjoint. Maybe another way of saying it. So yeah. So then now you can say, maybe we'll just make this back a list and then just write for I in range of length of P, right? From the first element, you can do a union of P sub 0 and P sub I. And that basically unions all the primes. And then now we could probably do them live, but I don't even think it's necessary anymore. I think we can do it again, right? What I mean is just do a second pass. For x in nums, yeah. So basically, yeah, okay. Yeah, we can maybe say, for example, a root is going to be, oh, I messed up. I don't know what I'm doing. I'm 20 minutes and I missed the adjacent number part. This is much easier, isn't it then? Because it's just stack, right? Alright, I am dumb. I am a Dumbo. I am a Dumbo. What am I doing? Alright, well, if you did want to solve I think it's actually interesting without the adjacent number, but it's too late for me to, but now I'm like, should I keep going or should I just finish the adjacent part? Okay, but yeah, I would say if you need enough solve it for if they're not adjacent, and this union find will get you most of the way there. All you have to do now is reconstruct the array from the union find, but this is not the problem, of course. So yeah, it's adjacent, and whenever you see Jason, you probably can just use a stack, right? So now you have because you repeat the adjacentness, right? So then now, yeah, if length of stack is greater than 0, man, this is equal to 0. I'm not even stack dot append x. Continue. Otherwise, stack dot. I guess we just do it anyway. I guess there are a couple ways to do it. And then while length of stack is greater than or equal to 2, and the top of the stack and the second top of the stack, if the GCD is greater than 1, then now we can pop, right? We can A is equal to B is equal to stack dot pop, and then now we want to replace that with the LCM. Which actually there is LCM now. I always used to write it by myself, but and this is no longer, yeah. And then now we can just stack dot back L, and we should be good, right? Yeah, I could have just misread this, but and then once I read it, it's like a 5-minute problem. I feel dumb, but if you wanted to upsolve the other way, definitely encourage you to. I feel very dumb. Yeah. I almost don't even want to explain this because I'm just like so demoralized for being dumb for like 19 minutes. But yeah, but I think if you see any two adjacent ones, the way that I think about it is that, yeah, you collapse, right? You're going to do adjacent one. So I don't know. I don't even know how to say it because I think this, without the GCD, LCM, GCD stuff, this is like I mean, it may even still be like a very basic stack problem. I don't actually know why this is graded as hard, other than if you're silly like me and misread it. I think part of that is that though. If it wasn't labeled as hard, I would not have missed it, maybe, because I would have thought the other one is too hard for a medium. But because it's hard, I was like, oh, because this is not hard. I don't know. I mean, yeah. Oh, I still got a wrong answer last time I did it. How did I get a wrong answer last time I did it? I think I was just being dumb and then use X because this has to be a while loop. Why would you do it this way, Larry? Why? Past Larry was a little bit dumb. Yeah, put it to the while loop. But yeah, this should not have been a hard. So I'm really confused, and that's why. Yeah, I don't know. All right. Well, this is linear time, linear space, right? Because every stack, every item, it will be on the stack once at most, either pushing or popping, and that's it. I'm dumb. That's what I have with this one. Let me know what you think. Thanks for watching. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.